So let's try another example, sort of from the real world with a different geometric shape. You are going to construct conical, meaning in the shape of a cone, coffee filters, or if you like, snow cone holders. These are things that you buy at the fair sometimes that hold, it's a paper cone that holds some ice with some flavoring in it. You're going to cut a sector from a circular disc of radius 8. So it's like this circle. You're going to cut out a sector here, and then you're going to glue those new edges together. So you can imagine if I cut out a very, very narrow sector here, I would get a cone that has very little height but is very broad. And if I did the opposite and cut out a very big sector, I would get a cone that is very tall but very narrow. Of all the different ways that I can cut sectors out, we'd like to figure out what's the largest possible volume that we can get. So, as usual, let's try to remind ourselves what our goal is. In this case, the goal is to maximize the volume. I think it's good to write out the goal if you're like taking an exam and maybe you start this problem and then you come back to it an hour later. It's easy to remind yourself what it is and not start to try to optimize the wrong thing. So the volume of a cone is 1/3 pi r squared h. Look at that. It's 1/3 the volume of a cylinder. Must be some nice geometry behind that you could look at. So as usual, the problem is that we have two variables here. So we need to get this down to just one variable. So let's put our variables on this picture here. So this is the radius of the cone. Is the radius of the cone 8? No. The radius of the cone will be less than 8 because I've cut some sector out of this and folded it together. So this r is not 8. We don't know what it is. And the height of the cone is this. That's h. So we must have some way to relate r and h using something else in the problem. Clearly, it's going to involve this 8, right? Where is the 8 in this picture? That's the question. Once you put the 8 in this picture, you can see what to do next. When we glue these two things together, I drew them as dashed lines. If I had drawn a dashed line here, that would be where the two were glued together. So this is the 8. So what else do we know? Looking at this picture, and I think we said once before, if there's only one theorem to know, what theorem is it? It's the Pythagorean theorem, right? So here we've got 8 squared equals r squared plus h squared. And in this case, it's not apparent which one would be easier to solve for. In fact, they're equally easy to solve for. But we need to look back to this. If I solve for h down here, I'm going to get a square root, and I'll be putting an r squared times a square root, and then that'll be sort of messy. I'll either have to use the product rule or combine them into one root and do the chain rule. On the other hand, if I just solve for r squared down here and put the r squared up there, we don't have any roots to deal with at all. So that'll be easier to do. So I'm going to bring the h squared to the other side. So h squared is 64 minus h squared equals r squared. So now we have the volume entirely as a function of h. So 1/3 pi r squared, which we just figured out is this, times h. As written, we'd have to use the product rule. If we want to save ourselves the trouble, I'm going to write this as just pi over 3. I can just multiply this h in, 64h minus h cubed. And now there's no product rule to deal with. So now we just take the derivative. All those derivative rules that we learned, they're coming in handy now, aren't they, to optimize all of these different situations. Pi over 3 is a multiplying constant. One of our rules says that stays. Derivative of 64h is 64 minus 3h squared. We want to find the critical points. So can this ever be undefined? It can't. This is just a parabola. Quadratic can never be undefined. So all we have to do is set this equal to 0. So one of these factors must be 0. Can pi over 3 be 0? No, pi over 3 certainly can't be 0. So it must be true that this is 0, meaning it must be true that 64 equals 3h squared. Right? That's what's going to make this 0. 64 minus 3h squared equals 0. Move the 3h squared to the other side. And then if I solve for h, I've got h squared equals 64 over 3. When I take the square root, I get 8 over square root of 3. If it bothers you to write a square root on the bottom, even though it shouldn't, as we've discussed earlier, go ahead and rationalize the denominator, as they say. We want to check, is this the what? Is this the max? We hope it is. So far, we've had good luck, right? These have always been what we were looking for. They've always been the max or the min, just what we wanted. Wonder if that's always going to continue. So 8 over square root of 3. This time I can plug in 0 on the left. So if I plug in 0 into v prime, I get a positive, which is what we hoped for. And if we plug in some number bigger than this, I think 7 is bigger than this, 64 minus 3 times 7 squared will give us a negative. So yes, it is. And now what did the question actually ask us for this time? It didn't ask us for the dimensions. It said, what is the largest possible volume? So the largest possible volume, how are we going to figure that out? It's v of this number, right? This is our formula for v, so v of 8 over square root of 3. So I want to plug this in, and I think it might be easier if we plug it into this top one here. So pi over 3, 64 minus v squared, minus h squared. But if I square this, I square the 8, I get 64, and I square the bottom, I just get 3, and then times an h at the end, times 8 over the square root of 3. And again, you don't need to simplify, but I think this one does end up looking reasonably nice. So let's see what happens here. We're going to get pi over 3 out front. 64, we want to get a common denominator. That should be 192. So we subtract that. We get 128 over 3 times 8 over the square root of 3. If you know your powers of 2, you know 8 times 128 is 1,024 pi. And on the bottom, 9 square roots of 3. And the units are cubic inches. It is very useful to know powers of 2. I think I know them up to 2 to the 16th. You don't need to know them quite that far, but if you do know them up to 2 to the 10th, you will find that it does come in handy in lots of situations, especially where you're trying to figure out things like investments doubling or populations doubling a certain number of times that they've doubled, then you can easily figure out. So 2 to the 10th means you've doubled 10 times, roughly multiplied by 1,000. You can get some pretty good estimates, and it's good at cocktail parties. We have an applet for this. If you haven't already looked at it, go and explore it and see that it should confirm what we have just found here.